All right, welcome to our next series in programming in Java. This is Eclipse Checkpoint 3. We call this an Affine Cipher. I just checked the pronunciation, and the internet's trying to tell me this is pronounced affine. This is an affine cipher. That throws me off, so I'm going to probably still accidentally call it affine for this whole video, and for that, I apologize. What does an affine cipher look like? The idea is, rather than using a Caesar cipher where we take the letter and apply a number, shifting it up the alphabet for encryption and down the alphabet for decryption, we've taken the whole alphabet and we've scrambled it now. And we've given a random letter to each of the 26 letters of the alphabet. And if you look at the PDF that hopefully I provided for you, you'll see that I took that alphabet and I scrambled it. So what it's going to look like is A was given randomly E, B was given K, C was given M, so on and so forth. This means that we have to be mindful of when I take a letter that I want to encrypt, I have to find where that letter is in the alphabet, right? If I was going to encrypt the letter D, I got to say, where is D on the alphabet? D is the fourth letter. All right, now I need to find the fourth letter of my letter map, which I see is F. And that's how this D right here in this particular test case became this F right there. Again, we ignore spaces. I'll show the test cases in action. How do you know you have a fully functioning affine cipher? It looks like that. Encrypt into affine. These letters pops out like that. What if I'm decrypting? Remember, the first token always tells us whether we're encrypting or decrypting. And I decrypt back out, and I get the signature Deadpool phrase, maximum effort. So how do I build this one? It's a little bit different than the first two checkpoints we did. We're going to use kind of the same concept that we've been using for our pseudocode so far, which is the program will fire up. We're going to take a message. We're going to send it down to a process command method. And then we're going to prime a loop with an empty string variable. I called mine return string. You can call it whatever you want. But we're going to go letter by letter addressing how do we change this letter, then the next one, then the next one. We'll use a for loop to traverse the entire string. We're going to grab each individual letter with, in previous videos, I'd said char at. And the reason I said char at was because it's very easy to switch from char to int, perform a shift, and then cast that int back to a char, and you can build out your secret message here. I think it might end up being easier to grab an individual letter with substring. You could do something like substring from I to I plus 1. That'll get you one particular letter. And we might want that individual letter in string format, and here's the reason why. The idea behind the letter maps, and I might as well go grab them right here. The idea behind the letter maps is I need to know when I get an input letter in, what is its location, so that I can figure out which letter of the output map I need to ask for. So to me, the idea is you've got the individual letter, then I'm going to go ahead and get the index of the letter in the alphabet. So how far is T into the alphabet? How far is K into the alphabet? Whatever it is. Then I'm going to ask for the letter at that index of the output letter map. So if I've asked for the jth letter, and the index of j is going to be, let's see here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, looks like. Well, if I've asked to encrypt a j, that means, and j is the index 9 character in the alphabet, then I have to get the index 9 character in the output map, which is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We see it's just below the J in the alphabet, so we would see that J becomes Z. So get the index of the letter in the alphabet, the letter I'm trying to translate, where was it? Go get the letter that's at that same index in the scrambled letter map. Then you can add that letter to return a string. And over the course of your for loop, you should visit each individual letter, ask for its location in the letter map, and then find where it is in the output. Now, decrypting is a little bit different. In decryption, you go the opposite direction. You're going to say, okay, what's your location in the output letter map? Say I'm looking for a Z. Z is not at the end of this map. It's all the way down here. It's in the index 9 position, which means it's going to, Z decrypts to J, just like a J encrypts to a Z. So you might think of the input and the output kind of swap when you are decrypting, because you're looking for the index in the output map, not the index in the input map to start with. So that's the idea behind an affine cipher. Students will ask, am I supposed to use this particular letter map you provided? Yes, and actually, spoiler alert, this is the letter map used by the rotor 1 rotor of the actual Enigma machine that was used in World War II, where A mapped to E and B mapped to K, C to M, and so on and so forth. So it actually has applications for later down the line. So that was checkpoint 3, Affine Cipher, indeed. Thanks for watching.